Hello and welcome to our new unit. Okay. In this unit, we are going to be doing applications of integrals. And in this first section, it's all about using the integral to talk about net change. In other words, a change over some usually time period. In the same way that we use the derivative to figure out the rate at which things were changing, we can use integrals to find kind of over some time as things were changing what the net change was. All right, so it's going to be fun. Okay, so listen, everybody loves chapter 6 as much as they love chapter 4. So if you remember, in chapter 3 we learned how to take derivatives, and then in chapter 4 it was all applications, word problems. Guess what? Okay, so now we learned how to take integrals. Chapter 6 is all about what are you going to use them for. So chapter 6 is where like integral word problems come in. Everybody loves a word problem. Okay, so the first kind of type of word problem we see with integrals is very similar. It's kind of the rest of the story that we saw in chapter 4 when we looked at linear motion. So if you remember in chapter 4, we learned that if you have displacement, you can take its derivative to get the velocity. My pen's not working. You can take the derivative to get velocity, and then you can take the derivative of velocity to get acceleration. We did that back in chapter 4. Well, now that we have integrals, which we know undo derivatives, we're going to be able to work backwards. So if they give us an acceleration, we'll be able to back it up and find an equation for velocity. We'll be able to back that up and find an equation for displacement. The only kind of piece of that that's tricky is, remember, when you have an integral, you have that constant of integration, right? Because if you take a derivative, you lose the constants. So if I want to go backwards from acceleration to velocity, they're going to have to give me some initial conditions. They're going to have to tell me, okay, at t equals, they might have to say like at v of 2 is 12, so at 2 seconds the velocity was 12. That's going to enable me to find out what my constant of integration was. And then if I want to go backwards from velocity to displacement, they're going to have to give me some initial condition for displacement. So tell me that, at 2 seconds, maybe the displacement was 10. Then I'll be able to figure out my C value. So working backwards has that added layer of having to figure out the constant along the way. We can't ever forget about that. But it's the same exact concept. Now, a lot of times what we see with AP in the open-endeds is they give us the velocity function. Because if they give you the velocity function, they can make you go either way, right? They can make you talk about acceleration, where you would have to take the derivative, and then they can also ask you about displacement or total distance traveled and make you go integral. So this is a really common open-ended type discussion. Usually on open-ended problems with integrals, the equation they give us is a rate, right? So that they can ask us for the total effect of that rate of change, which would be an integral, and they can also ask us like the rate at which that's changing, which would be a derivative. They like to be able to ask lots of questions about one function. If they give you the displacement, the only thing you can really do is a derivative, so that's no fun. Okay, so just quickly talk about why this is. If you remember, we know that the derivative of velocity is acceleration. So we can do this little separable differential equation thing, right? Take the derivative to the other side, or the dt, to the other side, and then all we have to do is integrate both sides. Right? So if we integrate both sides, we get velocity on this side is the integral of acceleration. And we could do the same thing with the rate of change for displacement. If you have a ds dt, which is velocity, if you integrate that, you're going to get displacement. All right, so again, it's just moving backwards. With derivatives, it's displacement, velocity, acceleration. Integrals takes us right back up the chain. Okay, let's take a look at an example, shall we? Okay, it says initially a particle has a position of s of 0 equals 9. So in other words, at t equals 0, we know that displacement is 9 meters. That's its initial position. Right? It says, what is the particle's position at t equals 5 seconds if its velocity function is given by. So here we go. They gave us a velocity function. Right. So I'm at 0 seconds right now. I want to know what's going on at 5 seconds. So if I want the displacement between 0 and 5, and notice I said the displacement between 0 and 5, not the distance. Okay, because it says what's the particle's position. It wants to know where it is. Okay, so I know where it started. If you can tell me that how it moved, did it move forward 5, did it move back 6, then I can figure out where it is. If they asked how far it traveled, that's a different question, right? Because that means that we don't want any cancellation in our integral. So if all they're asking for is its position, that's displacement, and we can allow for cancellation. All right, so displacement is going to come, I'm just going to make a random curve here. If this is my velocity curve, if I want the displacement between 0 and 5, all I need is the area under my velocity curve. Because my rectangles, if you think about it, are going to be meters per second high, and they're going to be seconds wide, and that's going to come out for an area in meters. So my integral is going to be a displacement. So if I want the displacement between 0 and 5, I just need to do the integral between 0 and 5 of t squared minus 8 over t plus 1 squared. Okay. Now listen, on the AP, this might very well be a calculator question, because honestly, on problems like this, what they're after is if you know how to go from velocity to displacement, not necessarily trying to figure out if you know how to do a definite integral, or maybe they just don't want you to take the time to do it. If it's a calculator question, you can absolutely go straight to the calculator, plug this in, get a decimal answer, and be done. Okay. For me in class, I tend to do them by hand if possible, just to kind of keep us fresh on doing integrals. But just FYI, if you're on a test, if you're on the AP, if you have your calculator, it is always okay to throw a definite integral into your calculator. They fully expect you to do that. If they want you to do it by hand, they'll make it so that it's a no calculator question. Period, end of story. But I like to do them by hand, just for practice. Oh, geez. Okay, hold on 1 second. I can't get to my pen when my picture is down there. Okay. All right, so let's do an integral here, right? So I need the integral of t squared is just t cubed over 3 minus 8, and I have the integral of t plus 1 squared. So this is a t plus 1 to the negative 2. There's my u. My du is just 1 dt, so no big deal. I just have to do t plus 1 to the negative 1 over negative 1. So that becomes plus, and then 1 over t plus 1, right? Because the integral of this is t plus 1 to the negative 1 over negative 1. And that simplifies to negative 1 over t plus 1. So we get this, right? And we just have to evaluate that from 0 to 5. All right, so here we go. This is the part where I do arithmetic. All right, let's plug in a 5. So that's 5 cubed over 3 plus 8 over 6. And then minus, we plug in a 0. So that is 0 plus 8. Very, very, very important to note that you still have to plug in the 0. One of the most common mistakes I see is people say they see that this is a 0 and they just assume that what's going to come out is 0. Don't do that. In this case, it comes out as an 8. Okay, so I've got 5 to the 3rd power, so that's 125 over 3, and 8 over 6 is 4 over 3, so that's what, 129 over 3 minus 8, which is 24 over 3. So I have 105 over 3, which is 35. I'm not going to lie to you, I put that one into the calculator real quick. I'm not that good at mental math. Okay, so the displacement from 0 to 5 was 35 meters, positive 35 meters. In other words, from where it started at 0 until it stopped at 5 seconds, it moved in the positive direction 35 meters. If this is multiple choice, I promise you 35 meters is going to be sitting there waiting for you to choose it because it's the wrong answer. Because you have to remember where it started. It started at 9. So it started at 9. It moved 35 in the positive direction. So our final answer is 44 meters. That's where it is at 5 seconds because it started at 9. Okay. Now, if this had come out negative, this would be a subtraction, right? It started at 9 and it moved back. Its net effect was moving back. That's fine. Don't go making it positive, right? The signs on these things mean something. So our final answer here is 44 meters. And again, it's just really important to note that initial condition. It's an easy one to miss. Okay, so that is the motion part of this. And again, it's not too far off from what we were doing in chapter 4 with relating displacement, velocity, and acceleration. It's just that now we're kind of moving both ways. So that makes those problems much more fun. Okay. Now, other than linear motion, what we see is integrals as what we call accumulators, right? So a function given to us as a rate, if I know something is moving, in motion, we can just talk about it in meters per second. That's an easy one. But it could be any rate. It could be liters of fluid per minute, whatever that rate is. So for example, let's call this gallons per minute, right? Let's say my rate given to me is gallons per minute. Right? If I have a nice steady curve, this is like an 8th grade math question, maybe not even 8th grade. Right? If they say, oh, something is flowing out, we're draining a pool, the water's flowing out at 7 gallons per minute, how much water is drained out after 10 minutes? We go, 7 gallons per minute for 10 minutes, that's 70 minutes, right? Or 70 gallons, right? And we know from calculus that what that really is the area under this curve. Now, that's a really fancy way to get that answer. When the rate is steady, we don't need calculus. But what we're going to see here, of course, because it's calculus, is a rate that isn't steady. Right? So we see these problems, they call them in and out problems, where you have a tank that's draining, but also there's water pumping into it. So you have this net effect of, it might be draining 3 gallons per minute, but it's pumping in 7 gallons per minute. So we say, okay, so overall we have 4 gallons per minute pumping in. So anytime you see a varied rate, that's when calculus comes in. Okay. One of the ways that they justify a rate varying is they say that there are several things plugged into a generator. Right. And so if only one of them is running, then it gets lots of power. But if 3 of them are running, they get less power. And so the rate at which these things are operating is constantly fluctuating depending on how many things are plugged in. Right? But they have to justify this variable rate. But the concept is the same. If I have a variable rate, if this is representing gallons per minute, and I want to know what happened between, I'm going to say 0 and 7 here, what I need is the area under this curve. Between 0 and 3, apparently it was losing, right? The rate was negative. And then from 3 to 7, the rate became positive. And we want to know what the net effect of that was, an accumulation. So here we're going to have a negative and a positive coming together. Now, there is no possible way for me to tell you every possible situation. They come up with the craziest scenarios, and you'll hear calculus teachers talking about them, like, oh, the banana problem, or the banana problem is a really famous one. It was something about bananas coming on down a conveyor belt. They come up with all kinds of random scenarios, but it is extraordinarily popular for AP to give us an open-ended question where the equation they give us is some rate at which something is changing, and they're going to ask us for some accumulation. After this many hours, how much was there? Or after this many hours, how many people were in the park? That's like the most basic standard question that we see every single year. Okay. So this is my most favorite depressing questions of those. It is about oil consumption. Okay. So it says, starting in 1980, the U.S. consumes oil at a rate sorry. Okay, there it is. At a rate of 27.08 e to the t over 25. Note that is an exponential function. So the rate at which we are consuming oil over time is increasing at an exponential rate. Way to go, America. Okay. All right. So, and this oil, by the way, is measured in billions of barrels. So whatever number we get out of this equation, it's that times 1 billion. It says find the total U.S. oil consumption from January 1st, 1980 to January 1st, 1990. Okay, so over a 10-year period. So if we call this T equals 0, then this will be T equals 10. Now, I want you to really be careful when you see problems like this. Sometimes they're super tricky. And I think this is mean, but I've seen it. They'll say January 1st, 1980 to December 31st, 1990. So it's really 11 years. So just be careful. You can't always just go with subtracting these two. Just make sure you pay attention. If they give you dates, make sure you pay attention to those dates. Or they could go to like end of June and it would be 10.5 or something. They're jokes. Okay. So this is the rate at which we are using oil. So if we integrate that, we should get the total amount of oil used, right? So if I take barrels per year and I multiply it by some measure of years, that's going to give me a total number of barrels, right? So in other words, if I take my equation and I go from 0 to 10, the area under that. This rate is barrels per year. The time change is years. This area is going to give me a number of barrels. So all I have to do is integrate this. So I've got 27.08 e to the t over 25. And I need to know from a time of 0 to a time of 10, what happened? What was the effect? All right, so again, this is absolutely, you could go to your calculator for this. We're not gonna, because why would we when we could do a quick U sub, right? Okay, so I have e to the t over 25, so there's my u, t over 25. So my du just needs to have a 1 over 25, which means I need a times 25 out here. It just keeps getting bigger, doesn't it? All right, so when I integrate that, I've got, let's see, 25 times 27.08. That's interesting. 677. The integral of e to the t over 25 is just e to the t over 25. And I'm evaluating that from 0 to 10. Again, don't assume that 0 is going to produce a 0. So grab a different color so it doesn't look as hard. All right, so let's go evaluate this up here. I've got to plug in a 10, so 677 e to the 10 over 25 minus 677 e to the 0 over 25, or e to the 0. All right, so should we get a number? All right, let's see. E to the 10 over 25 times 677. That is 1009.96532. That's what I see on my screen. I'm going to use, I'm writing that down, but I'm going to use the full number from the calculator. And then this is going to be minus, remember this is a 1, so minus 677. So minus 677. So I have 332.965 billions of barrels. So over that 10-year period from 1980 to 1990, the United States consumed, if you follow this model, almost 333 billions of barrels of oil. I don't know how big a barrel is, but I probably don't want to know. I also find this significant because this was between 80 and 90 before SUVs became really popular. I don't even want to know what this looks like today. All right, so again, we're going to look in class tomorrow at more examples of rates, right? Just the different ways they throw rates at us. But this is the basic gist. They give you a rate. You have to integrate to find an accumulation or a net effect over some period of time. It's usually the way it goes. All right. One last thing before I go, and that is if they give you data, right? So let's say they give you, they don't give you a function, right? They just give you a table of data that is points like at this moment the rate was 5, at this moment the rate was 10, at this moment the rate was 16, which they do sometimes. Okay. Absolutely, under no circumstances, even if it's a calculator question, should you go, you know what I'm going to do? I'm going to take that data, I'm going to run a regression on it, get me a function, and then integrate the function. Don't do that. You should never be running a regression on the AP exam. That's not a thing they ever ask you to do, right? It's not. Okay. So if you are given data, if you're given something like this, the answer is it's a RAM or a trap, right? What I need is the area under the curve. If I don't have a function, the best I can do is approximate. Okay? Now, you may want to graph it. If you like visual, you may be able to do it straight from the data in the table. But please, please, please do not waste your time and your energy calculating a wrong answer. You might be more accurate if you run a regression. They don't care about that. They care about you doing it the way they want it done. So under no circumstances, cannot stress this enough, should you be running a regression to try to find a function. If they give you data, we use the data. We're going to just do an approximation. So you'll notice here, again, this is one of the examples I was talking about earlier. Pump is connected to a generator that operates at a varying rate. So the pump is constantly getting a different amount of power, which means it's constantly working, changing the rate at which it can work. Okay. It says it's recorded in 5-minute intervals for 1 hour. So notice at time equals 0, it was pumping at 58 gallons per minute, and then it started doing better, and then it kind of went back down again, and then it started doing better again. So I can graph this if I want to be able to draw my rectangles and approximate, but all I'm doing is a RAM here. Now, this was a problem from the books that are not very specific here. They just say how many gallons were pumped during that hour. If this were the AP, they would have to be specific about whether they wanted you to use an RRAM, an RRAM or an LRAM, or maybe trapezoidal. But this is no doubt an approximation problem. No doubt. Okay, so we are going to talk tomorrow about all the different, just kind of practice with different types of problems like this, these rate questions, because they are very, very popular. But for now, that's all I've got. Have a wonderful day. Put any questions you have in the end of the video.